Now if we have a stable nucleus, that means that it wants to remain as it is. If we want to pull it apart, we actually need to put in energy to pull it apart. So the amount of energy that we need to put in to completely pull apart a nucleus is known as the binding energy. Now a useful thing to consider is the binding energy per nucleon. So this is how much energy we need to put in for each of the protons or neutrons found within the nucleus to completely cause that nucleus to come apart. So this graph here shows the binding energy per nucleon for all the different elements and isotopes. So the most stable isotope is iron 56. This has the highest binding energy per nucleon, and so per nucleon we have to put in the most energy to pull iron apart. So basically all the elements would really like to be iron. They all want to be as stable as possible. So the lighter elements will tend to undergo fusion, which means they'll tend to stick together to try and turn into bigger elements which are more like iron. The really heavy elements, on the other hand, like uranium, will undergo what's called nuclear fission, where they'll try and fall apart in order to make smaller nucleus, which is more like iron. So this is really important in nuclear power plants. It's how we get energy out of nuclear reactions. So this brings us on to some really exciting physics. We've discussed a bit about Einstein before, but one formula that Einstein is really famous for is E equals mc squared. So we're going to be seeing how to use that now. So when nucleons come together, they actually release energy because they're forming a more stable state. And when they release energy, there's actually a change in mass associated with this as well. So that amount of mass change is given by the formula E is equal to mc squared. So in this formula, E is the energy in joules, m is the mass in kilograms, and c is the speed of light in a vacuum, which is equal to 3.00 times 10 to the 8 meters per second. So let's look at an example now where we can calculate the mass defect and use this to calculate the energy that is released in an example of a nuclear reaction. So the question is, a 4,2 helium nucleus has 2 protons and 2 neutrons. The 4,2 helium nucleus has a mass of 6.6447 times 10 to the minus 27 kilograms, while a proton has a mass of 1.6726 times 10 to the minus 27 kilograms, and a neutron has a mass of 1.6749 times 10 to the minus 27 kilograms. A. Calculate the mass defect of 4,2 helium. B. Calculate the binding energy of 4,2 helium. C. Calculate the binding energy per nucleon of 4,2 helium. Okay, so to answer part A, we need to use the fact that the mass defect is equal to the mass of the constituents So that's the total mass of the protons and the neutrons that are combined in order to make the nucleus, minus the mass of the nucleus. Okay, so the constituents that go in, we have 2 of these protons, so this is 2 times 1.6726 times 10 to the minus 27, and then we've got 2 of these neutrons as well. So this part is the mass of the constituents, and now we have to subtract off the mass of the nucleus. So we're told the mass of the nucleus here, so this is 6.6447 times 10 to the minus 27, and everything there is in kilograms. And so solving this on the calculator, we get 0.0503 times 10 to the minus 27 kilograms is what's lost. So that's the difference between the mass of the protons and the neutrons and the mass of the nucleus. So this is going to be lost in the form of energy. But this here is called the mass defect. Now part B asks us to calculate the binding energy. So now that we've got the mass defect, we can use E is equal to mc squared in order to get the binding energy. So this mass here is the mass defect, so that's 0.0503 times 10 to the minus 27, and then times c squared, so 3.00 times 10 to the 8 squared, and solving that we end up with 4.53 times 10 to the minus 12 joules. Now, this is a very small number, and so often in nuclear physics, rather than using joules as the unit for energy, we use electron volts or either mega electron volts. Now, in order to convert from joules to electron volts, what we have to do is divide by E, the charge on an electron, which is 1.602 times 10 to the minus 19. So when we divide this energy by 1.602 times 10 to the minus 19, we get 2.83 times 10 to the 7 electron volts. And then if we wanted in mega electron volts, mega means times 10 to the 6, so this is equal to 28.3 mega electron volts. And so often this is a unit that is used to express these binding energies, just because it's more convenient. 28.3 is a nicer number than 4.53 times 10 to the minus 12 joules, or at least it's easier to visualize. And now part C wants our binding energy per nucleon, and so all we need to do is divide our binding energy, which is the 28.3 mega electron volts, by the number of nucleons. So this is equal to 28.3 on 4, because there's 4 nucleons, 2 protons and 2 neutrons, and so we have 7.06 mega electron volts as the binding energy per nucleon.